going to talk about something that hopefully starts making sense of why things are the way they are. What we're going to deal with is something referred to as impedance matching. If you've had AC, then you've heard the term impedance. If you haven't had AC, we'll talk a little bit about this, because this is a term you're going to be hearing often as far as communications and stuff like that. So here's our formulas that you should already know. These are power formulas. Voltage. This is Ohm's law. These are Watt's law formulas. We've come in, we're going to add a little bit about three-phase. So the advantage of three-phase is what we can do is that we know it takes at least two conductors to send power, right? If I add a third conductor and spread it out right, we can send 75% more power by spreading over three conductors that are out of phase. So here's your power formulas for three-phase. So it's V times I. So if you measure the voltage on one of your three-phase conductors, multiply it by that conductor, then you would multiply it by the square root of 3, which is 1.75. And that would give you the actual power being transmitted on all three phases. The problem we have with AC is if you had AC, we have devices in AC that we call capacitors and inductors. Now we create a capacitor just by having two conductive plates separated by some type of insulator. And when we put a magnetic field on this side, it basically creates a opposite field on the other side. Now the problem with these guys is their opposition varies with frequency. So a capacitor, and so notice on all my formulas, I didn't use R, I used what? Ohms. So all opposition in a circuit, whether it's reactive or resistive, is measured in ohms. The problem is with capacitors, we call the opposition FC, and it's equal to 1 over 2 pi FC. So capacitors, we don't buy them in ohms. We buy them in something called farads. So that would be the size of the actual number of farads. So if the farads go up and the frequency is the same, then X of C goes down, right? You'll see that because it's on the bottom. But if the farads stay the same and frequency goes up, then X of C goes down. So this guy, capacitors, the higher the frequency, the less opposition they have. And this is in ohms. This is in ohms. So that's why I've changed all these formulas instead of saying I is equal, V is equal to I times R. V is equal to I times the number of ohms in the circuit, whether it's reactive or whether it's resistive. Reactive means it varies with frequency. Inductors are nothing but coils of wire. And that's all it is. So every transformer has inductance. Every motor has inductance to it. And then, of course, we put them in there on purpose. This is called X of L, and it's equal to 2 pi FL. L is the unit of conductance, and this is in henries. So that means if you buy a capacitor, you won't see ohms. You'll say it's a 100 microfarad capacitor, it's a 10 microfarad capacitor, it's all that. So because why? Why don't they give it in ohms? Because so there's no such thing as a 100 ohm capacitor. There is a 100 ohm resistor, but there's not a 100 ohm capacitor. So we rate them in their ability to hold a charge. So how many coulombs they can store. And so these guys actually vary with frequency. Now you look, they're just opposite of each other. So one says I vary 1 over, the one says I vary with. So with inductors, as frequency goes up, opposition goes up, and if frequency goes down, opposition goes up. With capacitors, if frequency goes up, opposition goes down. If frequency goes down, opposition goes up. And this is why capacitors block DC. Because if you have a frequency of 0, then the opposition is technically infinity, which there's no such thing, right? It's just beyond what our meters can measure. If I put DC on an inductor, we got problems because now all we're dealing with is the resistance of the wire. So this is why an AC relay won't have near the number of wires or turns of wire as a DC relay. Because an AC relay can depend on X of L to get its opposition. A DC relay depends on the R of the conductor, right? You understand that? So if you ever look at the difference, if you put DC on an AC relay, it'll burn it up. It'll blow fuse. Because you don't get any X of L off of DC, right? You understand? If you put AC on a DC coil, you won't create a magnetic field strong enough to even fill it up because now you got all the X of L. So there is a big difference between DC relays and AC relays. So don't take for granted just because you find a relay that you can run it off DC or AC. Another problem we have is that these guys right here create what we call phase shifts. Eli the I thing. So this is AC. This is something you'll learn in AC, Eli the I. So what happens is that if we put AC in a circuit that has inductors or capacitive, it creates phase shifts between the voltage and the current in the circuit. One of them, so Eli says E is for voltage, by the way, so we know that E is another term. So in an inductive circuit, voltage leads current. In a capacitive circuit, current leads voltage. So they're opposite of each other. So one of them's going this way, the other one's going that way. And so if you vector them out and you put them in the circuit at the same time, at a certain frequency, they're going to cancel each other out, which is really cool. So if you ever have a real old radio or an old TV, which probably don't work anymore, you'll see that when you turn the dial, all you're doing is changing what we call a LC circuit. And at a certain frequency, they cancel each other out, and that lets the radio station go, which is pretty good. So this creates, if your voltage and your current gets out of phase with each other, it appears that you have more power in the circuit than you're actually getting work out of, and we call this apparent power. So they come up with, so we have what we call real power. So the power factor is equal to the work you're getting, or the real power, divided by the apparent power. So you pay for apparent power, but the work you're getting is real power. And we can compensate for this. We have dynamic power factor corrections where the ultimate goal is to get what we call a power factor of 1. That means the work that you're paying for is the work that you're getting. Huh? Well, you can get close. Out of U.S. Steel, they use synchronous motors. So the power grid is predominantly inductive because all your transformers are inductors, all your motors are inductors. Well, what we can do is we can add capacitors and it'll bring it back into phase. So this is every once in a while, you ever notice you're driving, you see a power coil up there and it's 3-phase and they'll have these 3 little cans up there and they're not nothing. Well, all they are is just capacitors. It's in there to do what? Try to bring the power factor back to 1. All the substations are they have a dynamic power factor correction. So what happens, it automatically shifts around and changes the capacitance in the circuit to correct for that. Your house is corrected for it, so you notice your house, when you get your power bill, it's kilowatts. So the power factor at your house is taken into consideration. Plants, they don't do that for you. So big plants like U.S. Steel, well, when I worked out there, when all the mills was running, their power bill was over $1 million a month. And they produce their own power. At the big blast furnaces and everything, those put out a gas that they could burn, and they'd put that into the power station, and they produce a lot of their own power. And they had one boss that his function in life was to maintain that power factor. Because what happens is that if you get below a power factor of like 95%, Alabama Power or TVA charges you a fee. And you think that's crazy, but their power, their generators, their transformers, everything has got to handle the power. So it's a lot cheaper for them if you maintain a good power factor to install smaller transformers, smaller conductors, smaller generators than it is for them to compensate for you having a very poor power factor. So there's a lot to this in AC. So anybody that tells you AC and DC are the same, they don't have any slightest idea. They are not the same. DC does not cause phase shift. Technically, if we could do it, DC would be more efficient to transmit than AC, because DC we don't have to worry about phase shift. We don't have to worry about capacitance. We don't have to worry about inductance. But the problem is it's really hard to step AC up and step it down. Now it's getting better with a lot of electronics, so there are some power grids now that are run on DC, and then they'll invert it and turn it back into AC for use. But it's just so dangerous. So the actual, in AC, it's actually apparent power times the power factor. That would give you the actual true power. So true power is the power that's doing work. Apparent power is what you're paid for. So power, we'll talk about this. Power is what we're paying for. We're not paying a current bill. We're not paying a voltage bill. We're paying a power bill. Power is work. Right? You understand that? And of course, we know the higher the voltage, it takes less current to deliver that power. We've talked about that several times. Conductors are used to deliver power in communications and power in communication systems. Similar to power delivery system, electrical sending information requires two electrical conductors. In DC circuit, the opposition to current flow is set by the resistance of the source and return conductor along with the load. In transistor amplifier circuits, there is an opposition to the input signal and output signal. We'll talk about this. In AC circuits, the opposition is set by resistance and reactance. And this is what we call impedance. But what you're going to find out is that in AC, normally they refer to the opposition as impedance. But it's in ohms. But usually impedance changes with frequency. So this is why it's imperative. We went down, we had the honor of going up to Alabama Power up in Birmingham, and went down to like 5 floors underground. That's where their main computer is. It's controlling the power grid. And they had one chart recorder that was showing the frequency, and it was a straight line, 60 cycles per second. 60 cycles per second. So maintaining the frequency is basically more important than maintaining the voltage. We could live with a variation with voltage, but they can't have a variation in frequency because everything is set on 60 cycles. All the impedances, all the phase shifts, all the capacitors, all that kind of stuff that they have corrected for that. All opposition is in ohms, period. And that's why when we move into AC, we should stop teaching B is equal to I times R. We should start saying B is equal to I times R. That's the way they should teach it in AC. Because in AC, we not only have in a resistive circuit, and that's where in a resistive circuit, when we say, so in a resistive circuit, if I put, this is what I'm getting at, if I put 120 volts AC, or if I come over here and have exactly the same circuit with nothing but resistors, and I come up here and I put 120 volts DC, that's what RMS is. So RMS says, I produce the same amount of work. 120 volts RMS would produce the same amount of work as 120 volts DC in a purely resistive circuit. If we come over here and we put AC on it, then we're dealing with a parent, that calculates apparent power. They don't calculate power, it calculates apparent power. So it creates phase shifts. So when you take AC, you're going to deal with a little bit of trig, but it's right angle trig. So you can use Oscar had a heap of apple delicate cells. And you create phase, and you it's under impedance. I don't know what's down there. Yeah, I should do one called impedance matching. So technically, the definition of impedance is opposition in a circuit, in an AC circuit that contains both reactive and resistive components. But like I said, just about all the time they talk about AC, they're going to talk about impedance.
I've heard impedance when people are like working like headphones, they'll talk about impedance. What is that exactly?
Well, the problem is in headphone, when they say it's an 8 ohm, if they say it's an 8 ohm speaker, if you put an ohm meter across that sucker, it's going to measure 5 ohms maybe. Because that is not a resistance, that's an impedance. Impedance for speakers is set at 1,000 hertz. So if you just put 1,000 hertz on a speaker and measure your current and your voltage, it would come up and give you 8 ohms. So that's an impedance, right? And this is what we're going to talk about. It's very, very important to understand things. So if you went out and got a speaker out of your car and put it on it, if you put it on the speaker, if you put it on a stereo in your house, you can also the car sounds good. The house sounds good. No. So our stereo systems are inside stereo systems with a lot of power. And they don't think that an 8 ohm cars are set on hold. So we don't get what we call it. In most amplifiers and communication systems, all types of opposition is called impedance. To some degree, everything opposes the flow of electrical current. A regulated AC or DC power supply appears to have zero impedance because they regulate it, right? So if the output tries to go down, they automatically raise it back up. And you can see it gets out of whack every once in a while. So we had a tree fall across one of our three-phase lines, and we had what we call a brownout because it exceeded, and the tree caught on fire. It was really cool. But what happens, it could not maintain that current, so the output actually dropped down. And what you're doing, you're actually seeing the impedance, the actual impedance of the system. Every AC/DC signal source will have an internal impedance or resistance. An internal impedance causes the voltage provided by the source to drop where the load is attached. Power is work, not voltage or current. The primary goal of an amplifier in communication channels is to get the maximum power transfer from the source to the load. That's their ultimate goal. So the cable company is sending their information through wires. Their ultimate goal is to get the maximum power transfer from their satellite station to your house. So this network cable, those yellow cables up there, that cable is designed to get the maximum power transfer from that switch up there to your computer. Impedance matching. Power transfer between the transmitter source and the receiver in a circuit is maximum when the impedance in the circuit matches. Every signal transmitter has some impedance. This is what causes the output voltage of a signal source to drop when it is connected to a load. On these function generators, it's got 50 ohms right there, so that's the impedance. So right now, if I was to take my scope and measure and hook it up directly to the output of this function generator, it would measure, and then I hook it up to a load, you'd see it do what? It would actually drop down. It's not regular. An example on the next slide, what we're going to do here is we're going to take a 10 ohm resistor, a 100 ohm resistor, and a 1K. So we're going to do DC, because it works for DC also, but you have to imagine this with an AC circuit too. So what we got is we got a signal source. And which of the following resistors will deliver the most power to a load when connected to a signal source with 100 ohms of internal resistance? What do you think, Cameron? Sam, what do you think, Candace? So what we're going to do is we're going to take a signal source, so it's going to be AC, and I'm going to come it up here, and this is going to simulate the internal resistance of the signal source. And it's going to be 100 ohms. And what we're going to do is we're going to come up here, and we're going to replace different resistors out there. So the signal source is going to have 100 ohms worth of resistance. We're going to use R because it's easier to calculate. We don't have to worry about phase shifts and stuff like that. And then I'm going to hook 3 resistors out there. I'm going to start off with a 10 ohm. Then I'm going to go to 100 ohms. Then I'm going to go to 1,000 ohms. So which one, Janice, do you think will get most power to the load? What do you think, Mario?
Well, based on the things that matching, I would say 100.
What do you think, Lee? What do you think, Alex? What do you think, Lee? What do you think, Alex? So here's our circuit. And we'll start off with 10 ohms. So here comes the 10 ohm resistor there. So calculate the power across the 10 ohms by the 10 ohms. So we got a simple series circuit, right? By the way, the simplest formula here is to use what we call the voltage divider formula. Saves you a calculation. So if we call this R, we'll call this RL. So VRL would be equal to 10 over 110. So it's R, it's the R you want, the voltage drop you want, divided by the total resistance, and then we'll multiply this times 10 volts. And then when you get your answer, don't do anything. When you get your answer, square it. So we're going to use the formula power is equal to V squared over R. So when you get your answer right here, don't clear it. Just hit the square key and then put divided by 10. And that'll give you the power. You could go through your total resistance, divide it into 10 volts. But we can do this with one swap of our calculator. And anytime you can save calculations, that's always best, right? So on my calculator, I would come up here and I would say 10 divided by 110. I just added those in my head, right? I'm going to say equals, then I'm going to multiply that times 10. So that's 909 millivolts. I'm going to square that, and then I'm going to divide it by 10. And so it's 82.6 milliwatts. However you do it. So that's why I know in these other power formulas, a lot of times saves you calculations. Huh? 82? Yeah. Well, what you're doing is so the voltage divider formula, this works for any series circuit. The actual formula is VRX in a series circuit is equal to RX over RT times DS. Source.
Are we doing it a different way? We will call it IR drop. If you would have to find a current, and then from the current, you can do the IR drop of the.
Yeah. So what happens though? You have 3 calculations. So we could do it this way. That's fine. So I could say 10. I could say 10 divided by 110, right? And then I could say, I could say, yeah, this is 10 volts. Then I can take the current and multiply that times 10 and come up with the current and then multiply it by the voltage. But what you're doing is you're adding another calculation. So what would happen, so what's this ratio right here? So 10, what's this ratio right here? Yeah, but it's a ratio. So it's 0.909. So it's not a milli, it's a ratio. Okay, so what happens if I come over here and change this to 25 volts? Well, what you do, you'd go through the whole thing again, but it would always drop 90.9%, 90.9%. So what you would do in DC is if I change the voltage on you, you'd go back and redo all the math, right? You understand? But that, in this circuit, this resistor right here will always drop 90.9% no matter what the applied voltage. So this works out. We call it the voltage divider formula, and what it does is saves one math calculation.
Okay, now, let's keep that 0.9 down here.
Then what you do is you pop it into this formula right here. Okay, so all when you do in your calculator, so now we're going to use power is equal to V squared over R. We're not going to use I because now that would add another calculation, right? You understand? So no of these other formulas, so I'll step it through again. Well, my calculator is still up here somewhere. So here's my calculator. This is the Windows calculator. And notice how many digits. It's a lot more. So I would take the resistor I want. I want the size of the resistor I want. I'm going to divide this by RT, which in this case it's pretty easy to do, right? So we're going to do it in 10. Right? I'm going to say equal. And then I'm going to multiply this by the source voltage. Okay, so that gives me V. So now I'm going to drop that. Now I'm ready. So that's V. So I should have put V out here, guys. I'm sorry. But you're right. No vote. I call it a ratio, but you're right. So now what I can do is I can come up here. I'm going to drop it into this power formula right here. So now all I have to do is hit the square key on my calculator. And then I can come up now, and then I can divide that by 10. And that gives me the power. So what we did is we basically did it with one formula. Instead of calculating I each time, right? So 83 milliwatts, I wound it up. So 10 ohms gave me 83 milliwatts to the load. And I need to come in and erase all this because all the calculations. So now y'all can do it for me. Okay, so now I've got the 100 ohm in there. So what would be the power delivered to the 100 ohm? So now we can say 100 divided by 200 times 10, right? Square that, divided by 100, and they'll give me the power. So anybody got it? $250 milliwatts? 250 milliwatts. So right off the bat, if you answer 10, you got it wrong. So 10, we only got 83 milliwatts. 100, we got 250 milliwatts. Because the impedance, the resistance of the load matches the resistance of the source. Okay, so now we're going to put our 1K up there. Right. So let's calculate the power delivered to the 1K. So that's going to be 1,000 divided by 1,100, right? Times 10 squared divided by 1,000. Well, one place I called it 83. Here I'm calling it 82. Who can see that? I need to go back into my animation. So what do we get here? It should be back around 83 milliwatts. So when did I get, and we can do this in tenths of ohms, we can do it in thousandths ohms, we can do it any way you want to, and we would always get the maximum power transfer when the impedances of the load matches the impedance of the source. So in a communication system, if I'm trying to get the maximum power transfer from my transmitter to receiver, I want all the impedances in the system to match. I had my father-in-law, his house was way back off the road. So they ran a cable to get his cable TV. It was a long run, and he was pulling a truck through there one day, a panel truck, and it broke. He got him a ladder, went out there and spliced it back together, and he had awful pictures. He had back when we used to broadcast and we had antennas on our house. He thought he could get a better picture. He had these rabbit ear antennas. He thought he could get a better picture if he hooked it up to his screen of his house. He thought it would be bigger, and he got an awful picture. Well, what he was doing, he was screwing around with what we call the impedance matching.
So you say impedance, that automatically says to mind that you're talking about
Ohms, right. Here we're doing R because X of L's and stuff like that would be. I could change this to X of L. I could change this to X of L. I could change it to X of C, and the math would be the same. It's just that here we understand. This would be true in a DC circuit too. But when we try to send signals, right now, guys, I am AC. Y'all understand that? In fact, by the way, this used to be very popular in spy movies, where they'd come into your TV and stuff, and they would just use the speaker. They would just use the speaker of the speaker as a microphone. Ooh. Let's see if something more. Hello? No, sorry. It's going to pick up a lot of noise. But this is just a microphone. It's picking up a lot of noise. So what I'm going to do is I'm using a speaker as a microphone. So what happens is it's got a magnet. And normally what we do is we put AC we put a signal into the electromagnet. It creates and then if we got a metal rod coming in from the top of the speaker. And when you put a magnet on there, it causes the metal to do what? To move in and out, and you bring that into what we call a diaphragm. And then the diaphragm creates sound waves. But what I can do is if I can talk into the speaker, it's going to cause the diaphragm to move. When the diaphragm moves to the magnetic field, it's going to generate, all that makes sense. So I can use a microphone. It's not very efficient, but I can use the speaker as a microphone. So what it's doing is generating AC signals, but it's got all these other frequencies composited on the top of that. So now that I've got it converted into electricity, I can use this into amplifiers, stuff like that, right? So you're looking at audio. So music is really neat because you got the bass is pretty constant, and then all the other frequencies are riding. It's a composite signal that are riding on top of it. And then what we do when we get to our speakers, if you've been into speakers before, is the speakers are set up, either you can run it through what we call equalizers, where you can gain, using these filters, using inductors and capacitors, you can set up gains in different frequency ranges. So most of y'all are interested in that in your car. You can make the bass sound louder, you can make it treble, you can do all kinds of neat stuff. Well, all you're doing is just rearranging these filters inside your. It's all electronic. But this is audio, guys. So if I'm going to get it, but it's not that audio is not near enough to run a speaker. So somehow we got to figure out how we can take a very low AC signal and do what? Amplify it, which is what we're trying to get into. So we gotta understand some things first. It's still kicking me off.
A transistor. Yeah.
Pebble transistors or whatever, and that's what we're fixing to get into.
Okay. That makes sense.
So, and this is these cables that we have. So this on the left, on the right, this is coaxial cable. And so it's got a center conductor, and then it's got a dielectric, and then it's got an outside conductor that we incorrectly call a shield, by the way. It is a conductor, but it's always referenced to earth ground. So that's your return conductor. This sets up capacitors and inductors right here, which creates what we call an impedance. So if you come up here and you measure between this conductor and that conductor, it would measure infinite ohms. If you come up here and you put a megahertz on this thing, it would have a certain impedance. So RG, I keep getting confused. I think the cable company uses RG58, which is 75 ohms. And then networking, we used to use RG59, which was 50 ohm cable. The old Twinplex, if you ever get into a house that's just got the antenna, that's 300 ohms. So used to when we moved over to cable, we didn't have a cable input onto our TV. All we had was the 300 ohm input. So you bought what we call a impedance matching transformer. So on one side it had an impedance of 75 ohms. On the other side it had 300 ohms. So that's another thing we can do with transformers, is we can literally match impedances. So 300 ohms and 75 ohms is very, very popular. Now TVs have a what? They have that 75 ohm input on. But if your coax cable ever breaks, you don't want to splice it together, right? You have special splicers that you have to maintain that impedance. Because if you don't maintain that impedance, then what? Then you don't have impedance matching, which means you don't get good signals anymore. They'll be really distorted.
I found that cut in my old house. Everything. That cable got cut in my old house. Everything just went out. Internet, phone.
Well, they came in and rewired mine a couple times. Because over time the cable gets degraded because it runs underground, and you lose your impedance matching, and you start getting really crummy pictures.
That's actually what I do for my part-time job. We do networking and houses.
Yeah, but when you do these splices and everything, they're precise. You got to do them right. Like this is twisted pairs, so this sets up inductance and capacitance between these two cables. This is 100 ohms, and that means if you ever did networking, you see people, they'll untwist it and put a big thing, makes it easier to splice. 1/4 inch is the maximum you're supposed to do, guys. When you put your connectors on there, but because if you get it out of that twist too far, you screw up the impedance of your cable. And so that might be a reason if you're at home and you got real bad network speed, is because when they put the heat system in there, they didn't do what? They didn't do it right. The problem we have is most of these networks are downwardly compatible, which means they try to communicate at the fastest speed. If they get garbage, they automatically do what? They automatically drop out. So these cables, impedance matching is very, very, very important. So we don't want a high impedance output amplifier connect to a low impedance input. So a lot of the things we do, and people can't understand in an amplifier why we go through stages. So we start off with a real high impedance because you have high impedance coming in on your input, and we move toward low impedance as we move toward your speakers. Your speakers have really, really low impedance. So impedance matching, when you go through all the science and math, what you need to understand is imperative, especially on these cables, these network cables, that you don't get this sucker out of a lot of twists. If they break, you don't go in there and untwist them and twist them together, right? After that, that's really going to screw up your network. Yeah, so we teach a case called cable splicing and installation. And also, if you take a PLC3, which is ILC 212, you actually make your own cable. Let me show you how to make these cables. Every single source transmitter has an internal impedance. Every conductor has an impedance. Every load receiver has an impedance. Maximum power transfer in the channel is achieved when the impedances in the channel match. That makes sense? Now,